morning everyone. Today I am going to discuss about the solar cell, which is another topic of the very important topic of the renewable energy resources, and it is the topic belongs to unit 1 of the renewable energy resources. So in the solar cell I will give you the introduction about the solar cell, what are the different types of solar cells and what are solar cell arrays, what are the characteristics and the parameters of the solar cell. So starting with the solar cell, it is basically a structure that converts the solar energy directly into the DC electric energy, right? It supplies a voltage and a current to the resistive load. And the resistive load basically includes the light, basically includes the battery or the motor, right? It is like a battery because it supplies the DC power. So this solar cell behaves like a battery because generally it provides the DC power, okay. Then we have to convert it into the AC power by using some batteries, by using some inverter, etc., right. So it is different from a battery in that sense that the voltage supply by the cell changes with changes in the resistance of the load, right. So solar cells are basically those which comprises of, which is composed of 2 or more specially prepared layers of the semiconductors. You can see here the layers of the semiconductor materials which are processed with an additive that causes the device to become the photosensitive. In these layers you can see one is the N type of material and another one is the P type of material are being used, and in between the N type and the P type, a layer is sandwiched between the N type and P type, and which can be called as the PN junction, okay. So by taking the sunlight from the sun, which will be reflected on this upper layer of the solar panel, right, electricity is generated because of the flow of the electrons in the holes, right. So when photons strike the surface of the solar cell, right, the electron hole pairs are released, generating the flow of the electricity. This is the principle on which the solar cell is working. So basically we can say that the solar cell is a transducer which basically converting the solar radiation or the sun rays into the electricity. So you can say that the solar cells are composed of various semiconductor materials. Mostly silicon material is being used for the composition of the solar cell, and the amount of the electricity generated from the sun, right, will vary from maximum to the zero. Maximum during the daytime, during the peak hours, peak sunshine hours, and zero definitely during the night time, right. So there are some applications in which it works satisfactorily during the sunshine, but the continuous supply of the solar energy is required, or the continuous supply of, due to the requirement of the continuous supply of the electricity, we need to store the solar energy, okay. For example, we can use the batteries to store the solar energy, right. And efficiency of conversion, the solar energy or the solar radiation basically depending upon the 3 factors. One is the reflectivity of the surface, another one is the absorptivity of the material which we have used this semiconductor material, and the last one is the rate of the generation and the recombination of the charge carriers, right. So basically these 3 are the main factors for the conversion of the solar radiation into the electricity. So we will talk about the solar cell, right, the single solar cell, how it is made. Basically it constitutes the 2 layers, N type and the P type, right. The most common solar cell is configured as a large area PN junction which is made from a silicon wafer, right. Single cell of the single solar cell will produce very little amount of electricity that you can only light up a small bulb or a calculator, right. So we need to so to acquire a large amount of electricity, we need to connect a large number of solar cells either in parallel or in series depending upon the application, right? So single photovoltaic cells are also used in many small electronics appliances such as watches and the calculators, right, and the batteries in the watches, right. So basically these solar cells are depending upon the working on the principle of photovoltaic operation, right, photovoltaic effect. So solar cells operate by converting the sun energy directly into the electricity by using the electronic properties of the material known as the semiconductor material. Generally silicon is being used over here for the generation of the electricity by using the sunlight, right. So basically the solar cells are composed of you can say semiconductor material. About 90% of the solar cells are using this silicon. Okay, we can in the 90% of the solar cells we are using the silicon, right. So basically it is divided into three categories, right, on the basis of the conduction of the electricity which is flowing through them. So these are the three types: the conductor, the insulator and the semiconductor. You can see the three diagrams over here. In this conductor you have the the two bands, the conduction band and the valence band, right, and the third one is the forbidden band. In case of conductor there is no forbidden band, while in case of insulator and semiconductor there is a forbidden band, right. So the electrons and holes can flow through the conduction band and the valence band depending upon the width of this forbidden band. So I'll discuss one by one. First of all, with the conductor, since it has no forbidden gap in between the conduction band and the valence band, so the energy also the energy in the both the bands are same, energy levels are same. So it is very easy for a valence electron to become a conduction electron, right. So in conductor, enough number of conducting electrons are present which are basically able to conduct electric current without the need of the external energy or the applied energy such as the light or the heat. But in case of insulator there is a forbidden gap, forbidden energy band, which is the gap between the valence band and the conduction band, and this forbidden gap or forbidden band is very large between the valence band and the conduction band. So it is not possible for the electrons to from the valence band to reach towards the conduction band. So there is no conduction of current in case of the insulator, right. In insulator the valence band, all the electrons are being occupied by the valence band while the conduction band is empty. So in this case there is no conduction of current. When we are talking about the semiconductors, the forbidden band, energy band, is very small than that of the insulator, but it is larger than that of the conductor. So because of the small forbidden gap, the valence electrons can easily move towards the electrons in the valence band can acquire the sufficient energy, right, and can easily cross the forbidden band and move towards the conduction band, right. So at room temperature only the semiconductors are capable of conducting the electric current and producing the electricity, right. Now talking about the semiconductor, where basically there are two type of semiconductors: intrinsic semiconductors and the extrinsic semiconductors, right. Intrinsic semiconductors are those which are extremely pure, right, where the number of free electrons is always equal to the number of holes. While in case of the extrinsic semiconductor, some type of impurity is mixed in it, right, so as to increase the conductivity of the semiconductor, right. So talking about the extrinsic semiconductor, basically it is of two types, the N type and the P type, right. In the semiconductor, since I have told you that in the extrinsic semiconductor we make some type of impurity. So in case of N type extrinsic semiconductor, we makes the pentavalent impurity, such as arsenic, antimony, or the phosphorus, right? When this pentavalent impurity is added to the silicon, right, the impurity atom will form a covalent bond between the silicon atom, right? But since intrinsic semiconductor have only 4 electron and 4 holes in their valence shell, 1 space electron so produced will for each impurity atom and it. Okay? So here in case of n type extrinsic semiconductor, the majority are the electrons and the minor holes are the minority charge carriers. When we are talking about the p type of the extrinsic semiconductors, a small amount of trivalent impurity is being added. For example, the boron, the aluminium, the indium, the gallium, right? It is added to the pure semiconductor material during the crystal growth, and which results in the p type of the extrinsic semiconductor. So you can see here the photovoltaic effect, the generation, light energy is being falling on the upper surface of the n type semiconductor, and the 2 conductors are there, p type and n type, and a layer is being formed in between. The junction is called the p-n junction. So with the help of the electricity is being generated with the flow of the electrons and the holes, and we can define the photovoltaic effect as the generation of voltage in the p-n junction in a semiconductor due to the absorption of the light radiation called the photovoltaic effect, right? So the device based on this effect is called the photovoltaic device. So what are the different types of the solar cells, right? So based upon the crystal used, solar cells can be divided as monocrystalline, polycrystalline, amorphous silicon, right? So the monocrystalline silicon cell, it is produced from the pure silicon, that is from a single, mono is representing a single crystal, that a single crystal is being used for the production of the monocrystalline silicon cell, right? Single monocrystalline cell is basically pure and basically defect free, so the efficiency of the cell is very high, right, in case of monocrystalline silicon cell. When we talk about the polycrystalline solar cell, it is in this liquid silicon is used as a raw material, right? And polycrystalline silicon was obtained followed by the solidification process, right? So the material which contain various crystalline sizes, right? So the efficiency is less than the monocrystalline silicon cell in case of the polycrystalline solar cell. And when we talk about the amorphous silicon, which is obtained by the depositing the silicon film on the substrate like a glass plate, right? So the layer thickness amounts to be less than the 1 micrometer, and the thickness of the human hair for comparison is about 50 to 100 micrometer, while in case of amorphous silicon the thickness is just 1 micrometer. So you can compare obviously, and the efficiency is much lower than that of these 2 types. Highest efficiency is this, then it is lesser than this, and it is the lowest efficiency type of the solar cell, right? So they are basically using the where the low power is required, for example the watches, the calculators, etc., right? Now what is the solar cell array? If a photovoltaic solar panels are made up of individual photovoltaic cells connected together, then the solar photovoltaic array, also known as simple solar array. You can see this is the solar array. Here one cell, this is one cell, and large number of cells when combined is formed a module, a single module, and when some modules are combined together will form the solar array, right? So solar array is a system which is made up of group of solar panels connected together. This is, you can say, a module or a solar panel which is formed by combining the lots of solar cell in it, and when the large number of solar panels are combined together, connected together, then it will form the array. right? So a photovoltaic array is therefore multiple solar panels electrically wired together or connected together to form a large panel PV system, right? And in general, the larger the total surface of the array, the more solar electricity will be produced in case of solar panels. See, same process has been shown here, that this is a single solar cell and a large number of solar cells are connected here in series, you can say, to form a PV panel. And when a large number of individual PV panels are connected through wired together, then they form the PV array, solar array also. So basically a solar cell is the basic building block of the solar panel, right? So each cell produces approximately half volt of, and a solar module can have a number of solar cells. A solar module designed for charging a 12-volt battery will typically have how much? Around 36 solar cells, because one solar cell will produce around half volt, right? While the typical residential grid connected system uses about 60 solar cells. Okay. For large commercial and utility scale solar system, the solar modules will have 72 solar cells, and by increasing the number of solar cells, the module voltage and voltage can be increased. So from here you can see we have formed the solar panel, and from solar panel we can obviously connect the can form the solar array, right? So most solar cells which are manufactured today are approximately of the size of 6 by 6, right? Small custom solar modules will contain solar cells that are being cut into smaller sizes. For example, if a full size of solar cell produces around 10 amperes and it is cut into half of it, will now produce only 5 ampere. As the solar cell is cut in half, its typical voltage remains unchanged, that is half a volt for each cell. So basically the solar size of the photovoltaic array can consist of individual PV modules or panels which are connected together in an urban environment and mounted on the rooftop, and may consist of hundreds of PV panels which are connected together in a field so as to supply power for a whole town, right? So the flexibility of the modular photovoltaic array allows designer to create solar power system that can meet a variety of electrical need, no matter how large or how small are they have made. So you can see some examples over here that the solar panels are connected over here, solar arrays on the ground mounted rack array, pole mounted tracking array, building integrated also nowadays we are using, and obviously the roof mounted array are being used to collect the solar energy and convert it into the electricity. Now the characteristics of the photovoltaic array. So it is important to see that the photovoltaic panels or the modules from the different manufacturers should not be mixed together, right, in a single array, even if their power ratings, voltage or current ratings are same, right? This is because the differences in the solar panels characteristics, IV characteristics, as well as their spectral responses are likely to produce the mismatch losses within a array. So which will reduce definitely the efficiency of the overall panel, right? So the electrical characteristic of a photovoltaic array are basically summarized on the basis of output current and the voltage. The amount and intensity, right, of the solar insolation or the solar irradiance controls the amount of the output power, and the operating temperature will affect the output voltage of the PV array, right? So basically the characteristics are depending upon the output voltage and current. Output current is depending upon the intensity of the solar radiation, while the output voltage is depending upon the operating temperature of the array. So what are the parameters we will consider is the open circuit voltage over here, short circuit current and the maximum power. So open circuit voltage is the maximum voltage that an array can produce when the terminals are not connected to any kind of load, right? So this voltage is as much as higher, that is, you can say V max, which can relate to the operation of the PV array, right, which is basically fixed by the load. So value of the number of PV panels connected together in series will be will responsible for this value of the open circuit voltage, right. And the maximum current provided by the PV array when the output connectors are shorted together, right, that just like a short circuit condition, then this value is much higher than the maximum current, which basically relates to the normal operating circuit current, right. And the maximum power point, this relate to the point where the power is supplied by the array is connected to the load, right, and it is at the maximum value, which is given by P max is equals to I max into V max. And the maximum power point of a photovoltaic array is measured in terms of watt or peak watts. So another factor are the percentage efficiency and the fill factor. So fill factor is basically the relationship between the maximum power of the that the array can actually provide under normal operating condition and the product of the open circuit voltage times the short circuit current, right. So this fill factor values give an idea of the quality of the array, and its value will be much closer to the unity, right. The more power the array can provide, right. So the typical values are around between 0.7 and 0.8, right, and it must be around unity. And percentage efficiency is the efficiency of photovoltaic array is the ratio between the maximum electrical power that the array can produce compared to the amount of the solar irradiance which are hitting the array, right. So the efficiency of the solar array is around 10 to 12%, which is depending upon the cells, which type of cells we have mounted, right, which type of cells we are using, either monocrystalline, polycrystalline or the amorphous one, right. So these are the connection you can see in the solar cell array. So they are following the photovoltaic IV characteristics, right, which basically provide the information about the designer need to configure the system, which can operate as close as possible to the maximum peak power point. You can see here 4 solar panels are connected over here. Okay, these two are connected in series, further these two are connected in series, and the overall is connected in parallel to each other, and a single panel is providing around a 12 volt, right. So the combined voltage will be across this photovoltaic array will be 24 volt, and the current will be definitely, for the combined current will be the addition of the two currents, which is coming from first and the second panel, right. So you can see here the peak power is measured as the PV module produces its maximum amount of power when exposed to solar radiation, which is equivalent to 1000 watts per square meter, right, or you can say 1 kilometer per kilowatt per meter square. This is the circuit for the formation, right. So simple photovoltaic array above consists of, basically here you can see the 4 photovoltaic panels which are producing the 2 parallel branches, one in which in one branch the 2 panels are connected in series, right. And this is the voltage I have, output voltage will be around 12 volt, and the current produced by a single panel is 3.75 ampere at the full sun, right. So the total current will be 3.75 plus 3.75 will be equals to the 7.5 amperes, and we can calculate the output power which is obtained from the voltage and the current. 24 into 7.5 is coming out to be 180 watt from this panel solar array, right. So these are the characteristics. So you can see over here the voltage characteristics along the IV characteristics, and this is the power versus the voltage characteristics. So we have the maximum power over here is 180 watt, and when the sun is full, right, and because the maximum output power of each panel or the module is equal to 45 volt, that is 12 into 75, 3.75. So due to different levels of the solar radiation and due to the temperature effect, electrical losses, etc., so real power, right, maximum power is usually very less than the 180 watt, right. So we can draw these two characteristics depending upon the, this is the maximum power reaching around the 24 volt, right, and the, here you can see the open circuit voltage is around 24 volt when we are having around 7.5 ampere current from the two panels from the complete array. It's all today's lecture. Thank you so much.